Hi, so today we're going to be talking about energy transfer, and this is a little bit of the chemical background behind why the energy we'll be talking about moves through the different systems as it does in biology. This corresponds with section 7.1 in your textbook. So if you recall, catabolism is the breaking down of substances, and these catabolic pathways in biology typically involve electron transfer, and this is one of the central processes for cellular respiration, which we'll be learning about next. So that's why we have to talk about this. Looking back to types of pathways, remember catabolic pathways take a large substance and break it down into smaller substances, and these catabolic processes also release energy, meaning they're exergonic. That's important to remember. There are two different examples we'll be talking about related to catabolism. One is fermentation, and this is when there's a partial breaking down of sugars, and this occurs without oxygen. So sometimes we call fermentation anaerobic respiration, respiration without oxygen. On the other hand, aerobic respiration requires oxygen, and this consumes organic molecules and oxygen, and then we end up with carbon dioxide, water, and especially, most importantly, ATP. So they're very similar processes overall, so we'll talk about both of them, but anaerobic respiration, because oxygen isn't available, uses other things. So fermentation uses a different reactant. Technically, cellular respiration refers to both the aerobic and anaerobic process, but most of the time we use it to refer to the aerobic process, and that's how we'll be talking about it throughout the rest of this unit, so keep that in mind. And when we talk about organic fuel being broken down in cellular respiration, you might be thinking to yourself, well, what is fuel? All of the things that we've talked about so far in terms of macromolecules, including carbohydrates, fats, and proteins, are consumed by us as fuel. However, we typically see that carbs and lipids are used as fuel more often, and we'll explain why that is later on in this lesson. And we also typically, when we're learning about cellular respiration, trace the reaction using glucose as the model fuel. However, you could replace glucose with several other different components, but for our cases, we're going to talk about glucose, and the breakdown of glucose is an exergonic process. And as you can see, that's true because it releases energy in the form of both ATP and heat. So something that is going to be new to you is something known as redox reactions. And this is just a combination of the two words oxidation and reduction. So these type of reactions are all about electron transfer. The reason why energy is released is because we are moving electrons from one substance to another. And this released energy, if you recall from the ATP hydrolysis lesson, is what's used to regenerate ATP once it's been converted to ADP and used. So a redox reaction is any reaction where there is one substance transferring one or more electrons to another substance. And sometimes they're called oxidation reduction reactions, but to make it quick and easy, we call it redox reactions. So in an oxidation process, this is when there is a loss of one or more electrons by a substance. And we say that the substance losing the electrons has been oxidized. When we have reduction, that is a result of when one substance gains one or more electrons, and this is the adding of electrons, and we say that this substance has been reduced. And the reason why it's called reduction is because if you think about it, when you add electrons to a substance, you're adding negative charge, and this reduces its positive charge. So when you add electrons, that's when the charge is reduced, so we say the substance has been reduced. In this picture, you can see this is not a biology reaction, this is a chemistry reaction, but when salt, it becomes ionized into its ions, sodium becomes oxidized because it loses an electron, and that's why it becomes positively charged, and chlorine becomes reduced. It gains this electron. So we are adding the electron here, and that's why it's been reduced. This is kind of a more general equation where we have one substance that becomes oxidized loses an electron, and one substance that becomes reduced and gains an electron. And the electron donor, the one that is becoming oxidized, is sometimes referred to as the reducing agent, because it's the one that's providing the electron for the other to be reduced. And then this other guy, the one becoming reduced, the electron acceptor, is often known as the oxidizing agent. So if we go back to this slide, in this one, sodium would be our reducing agent because they're donating the electron, and chlorine would be our oxidizing agent because they are kind of receiving the electron there. So that's kind of a little bit, hopefully not too confusing, but that's, in case you hear that terminology, that's what it means. So once again, the electron donor, reducing agent, electron acceptor, oxidizing agents. And we're going to go ahead and move toward talking about cellular respiration a little bit more. So redox reactions always happen together, and one other way that you might see redox reactions happening is through the transfer of hydrogen atoms. When hydrogen atoms are transferred between different molecules, this results in oxidation because the hydrogen atoms involve the transfer of electrons. So if we take a look at an example of cellular respiration, we can see here the glucose molecule is becoming oxidized because in the following product it has lost the hydrogen atoms. In other words, it's lost electrons. And then over here, our oxygen has gained a hydrogen, and that indicates to us that it's gained an electron. And this is an important thing to note. So the reason why that is because a hydrogen atom is really a proton plus an electron. If you take away an electron from a hydrogen, it just becomes H+, which is a positive +1 charge, which is the same as a proton. So whenever hydrogen atoms are moving around, that usually also means that electrons are moving around. So that is why in cellular respiration we can tell that the glucose is being oxidized and the oxygen is being reduced. And if you remember at the beginning of the lesson, I mentioned that we typically use carbohydrates and fats as our fuel, and that is because if you remember from the first unit, they have carbon, hydrogen, and oxygen, and lots of hydrogens. So because of all of those hydrogens, lots of electrons are able to be transferred, which gives us lots of energy that can be used to make ATP. So one way you can remember redox reactions is by remembering the mnemonic oil rig. Oxidation is loss and reduction is gain. And if you want to pause on this page, this just gives you another example and a little bit of a picture. So when we are talking about breaking down glucose, one of the most important things to remember is that our reactions often have to be coupled together. And we typically will use ATP and something called NADH to couple these reactions and get us the energy we need. So when we're talking about the NAD+, this is a pretty common substance used in cellular respiration. Glucose and other organic molecules are broken down in this series of steps, as you recall. And where we get the energy for this comes from the transfer of electrons. And the electrons from organic compounds are usually transferred first to NAD+, which is a coenzyme that helps the enzymes for each step of the breakdown of glucose take place. These electrons often travel, as I mentioned, with a hydrogen atom or a proton, and that's where they get passed to NAD+, which acts as an oxidizing agent, and it is then reduced and becomes NADH. So there are enzymes that help facilitate this process as well, but the important thing to note is that in the reduction of NAD+, there are a transfer of 2 electrons and 1 hydrogen ion to NAD+, and one of the hydrogen ions gets released. So this is NAD plus right here, but if we want to look in at this particular place, you can see when we are trying to break down our fuel and reduce our NAD plus, there is this transfer of electrons, as you can see. The dehydrogenase facilitates this reduction, and you can see we end up adding a hydrogen here to our NAD+, which removes this positive sign because we're also adding 2 electrons to the system, which help to neutralize the charge. And this reaction is highly endergonic. It requires a lot of energy to happen. And the reason why that's important is that in the cell, oxygen is highly electronegative and is readily able to accept electrons from NADH to oxidize it. So once this has happened and we end up with NADH, the oxygen likes to quickly accept those, and this is a highly exergonic reaction, and that's what releases the energy to fuel ATP hydrolysis. So this reduction of NAD plus to NADH, like I said, is one small step, but what really gives us the energy is then the oxidation of that by the oxygen molecules in the cell. So in typical reactions, this is a very explosive experience with the addition of oxygen, but in cellular respiration, we break this up into a series of smaller steps in something called the electron transport chain, which you'll learn about. And so this breaks the fall of electrons energy level into several intermediate steps, and this is all facilitated by proteins in the inner membrane of the mitochondria. And how this works is NADH, NADA, the reduced form of NAD+, shuttles electrons to the top of the chain. They slowly move down, and then finally at the bottom they're captured by oxygen, and then we add hydrogen, and this ends up resulting us in water. This is essentially similar. Electrons travel down this similar to how gravity pulls objects down from the sky. Each step has lower energy and is thus more stable than the previous step. So it's just trying to move the electrons to a more stable state slowly but surely. And this gives us small bursts of energy in the form of ATP. And so that's a little bit about how NAD plus is involved, but just keep in mind in all of the further sections in this unit, electron transfer will be very important.